Out there, in the endless black of space, drift the loners of the cosmos, rogue moons, and lost suns, celestial orphans cut loose from the worlds they once called home. Picture a solitary moon, adrift in the void, no planet to circle, no star to warm its surface. It moves through the darkness like a ghost, untethered and silent, a wanderer in a universe that seems to have forgotten it exists. These cosmic outcasts defy everything we thought we knew about how celestial bodies behave. They challenge the very laws of gravity, the rules of formation, and even our understanding of where life might hide. How does something as fragile as a moon survive alone in the freezing expanse between stars? What secrets might these orphans carry about the origins of the universe itself? This is a story of mystery and wonder, of celestial rebels that refuse to follow the script. Astronomers once believed moons and planets were bound together by an unbreakable cosmic order, but rogue moons and lost suns tell a different tale. They whisper of chaos, of collisions and near misses, of gravitational slingshots that sent them spinning into the unknown. Some may have been torn from their parent worlds by violent encounters, while others might have formed in the depths of space, never knowing the warmth of a nearby star. And yet, against all odds, they endure, floating through the darkness, silent witnesses to the universe's untold stories. Today, we're setting out on a journey to uncover their secrets. We'll explore how these cosmic orphans were discovered, what makes them so extraordinary, and why they might hold clues to some of the biggest questions in astronomy. Could a drifting moon, lost in the void, still harbor the ingredients for life? Might a wandering sun, long separated from its planetary family, rewrite the history of how solar systems form? The answers are out there, waiting in the dark, so let's step into the unknown together and discover the incredible tale of these celestial wanderers, the orphans of the expanding cosmos. What exactly makes a celestial body an orphan of the cosmos? Unlike the planets and moons we're familiar with locked in predictable orbits around stars or larger worlds, rogue moons and lost suns exist in a state of cosmic exile. A rogue moon begins its life as a typical satellite, circling a planet just like our own moon does Earth. But somewhere along the way, a violent encounter, perhaps a collision with another object or a gravitational kick from a passing star, hurls it free from its orbit, sending it tumbling into the void. Suddenly, it's no longer bound to anything, drifting alone through the freezing darkness, untethered and unmoored. Then there are the lost sun stars that once burned brightly within galaxies, only to be torn away by immense forces. Picture a star ripped from its home during a galactic collision, flung into the emptiness between galaxies with nothing to light its way. These stellar wanderers move through the intergalactic void like ships without ports, their light fading into the abyss. Spotting them is like searching for a single candle in an endless night. Their faint glow often gets lost in the glare of brighter, closer stars, making them some of the most elusive objects in the universe. The mere existence of these cosmic orphans forces astronomers to rethink what they know. If moons can be ejected from their orbits, how often does this happen? Could our own moon one day break free? And if stars can be flung from their galaxies, what does that mean for the stability of the cosmos? These questions aren't just academic. They challenge the very foundations of how we understand planetary systems and galactic evolution. Every rogue moon or lost sun we discover is a clue, a piece of the puzzle that could rewrite the story of our universe. Their loneliness holds secrets, and those secrets might just change everything. The hunt for rogue moons began with an astronomical puzzle, objects that shouldn't exist, drifting where no moon was thought to survive. For centuries, astronomers assumed moons stayed obediently bound to their planets, following predictable paths. Then came the first whispers of something strange, faint, fast-moving dots in deep space that didn't match any known asteroids or comets. The breakthrough came with modern telescopes like the Hubble and later the James Webb, equipped with infrared sensors capable of spotting these cold, dark wanderers against the blackness of space. These instruments revealed the truth: moons weren't always loyal satellites. Some had gone rogue. One of the most compelling examples lies in our own solar system's history. Jupiter, with its immense gravity, may have once hosted dozens more moons than it does today. During the chaotic early days of the solar system, as planets jostled for position, gravitational tugs of war could have sent smaller moons careening into space. Computer simulations show that a close encounter between two moons might have provided enough energy to fling one free, like a slingshot firing a stone into the void. Other candidates include moons ejected during planetary collisions. Imagine the cosmic wreckage of two young worlds smashing together, their shattered fragments cast adrift. But how do we spot something as small and dark as a moon floating light years away? The answer lies in a technique called microlensing. When a rogue moon passes in front of a distant star, its gravity bends the starlight ever so slightly, creating a telltale brightening that telescopes can detect. It's like finding a needle in a haystack by watching for the moment it casts a shadow. Early astronomers like Johannes Kepler speculated about wandering stars unattached to any system, but without the tools to prove it, the idea remained science fiction. Now, with advanced tech and patient observation, we're uncovering these cosmic escape artists one by one. Each discovery rewrites the rules. Take the case of a potential rogue moon spotted in 2019, drifting near the edge of our galaxy. Its speed and trajectory suggested it wasn't just a stray asteroid. It moved like something that had once orbited a planet before being torn away. Then there's the baffling example of a moon-sized object found in interstellar space, its composition hinting at origins around a gas giant. These findings paint a picture of a universe far more dynamic and violent than we imagined, where celestial bodies are constantly being reshuffled, ejected, and set adrift. The cosmos, it seems, has a habit of losing its children, and we're only just beginning to find them. While rogue moons tell the story of planetary systems in chaos, lost suns reveal an even grander drama: the explosive forces that can fling entire stars out of their galaxies. These hypervelocity stars race through the void at millions of miles per hour, their trajectories so extreme they defy the gravitational pull of everything around them. Imagine a star born in the crowded heart of a galaxy, suddenly catapulted into the emptiness between galaxies like a spark flung from a bonfire. Its light, once one among billions, now shines alone in the unimaginable vastness of intergalactic space. The most likely culprit behind these stellar ejections, the monstrous gravity of supermassive black holes. When a binary star system, two stars orbiting each other, wanders too close to a galaxy's central black hole, one star may be captured while the other gets slingshotted outward at breathtaking speed. It's a cosmic game of gravitational pinball where the loser is hurled into the abyss. Other hypervelocity stars might be relics of galactic collisions, flung free when two galaxies merge in a chaotic dance of stars and dust. There's even evidence some could be survivors of dwarf galaxies torn apart by larger neighbors, their stars scattered like debris from a shipwreck. What's astonishing is how these runaway stars carry clues about the invisible scaffolding of the universe. As they streak through the darkness, their paths bend ever so slightly under the influence of dark matter, the mysterious, unseen substance that makes up most of the cosmos. Like breadcrumbs trailing through a forest, Their movements map the hidden contours of dark matter's gravitational web. The faster the star, the farther it travels, offering astronomers a unique probe into regions of space where normal telescopes see nothing at all. Consider the story of one hypervelocity star discovered in 2005, racing away from the Milky Way at over 1.5 million miles per hour. Spectroscopy revealed it was rich in heavy elements, suggesting it originated near our galaxy's core, where supernova forged such materials. Another, spotted in 2019, was moving so fast it had already crossed 200,000 light-years of intergalactic space, a distance so vast most stars would take billions of years to traverse it. These stellar fugitives don't just wander, they flee, their incredible speeds etching escape routes across the cosmos. Yet for all their isolation, lost suns aren't entirely alone. Some may still harbor planets dragged along in their gravitational grip. Picture a world orbiting one of these exiles, its sky devoid of neighboring stars, its night illuminated only by the faint glow of distant galaxies. Could life persist under such a lone sun? It's a haunting possibility that even in the deepest voids, the universe might still find a way to nurture existence. And as these stars continue their endless journeys, they remind us that the cosmos is far wilder, far more unpredictable than we ever imagined. Dark matter, the invisible force shaping the cosmos, may hold the key to understanding why so many celestial bodies end up exiled in the void. While black holes and galactic collisions can hurl stars and moons into the darkness, there's growing evidence that dark matter plays an equally dramatic role in these cosmic ejections. Picture a vast, unseen halo of dark matter surrounding a galaxy, its gravitational fingers tugging at everything within reach. Stars and moons don't just drift away randomly, they're often pushed by forces we can't even see. Recent supercomputer simulations reveal how dark matter's uneven distribution could act like a hidden slingshot. When a star or moon ventures too close to a dense pocket of dark matter, the sudden gravitational kick might send it careening out of its orbit. Think of it like a roller coaster hitting an unexpected drop. The object gains enough speed to break free entirely. Some theories suggest entire dark matter filaments, stretching between galaxies, could funnel these orphans into the void like cosmic rivers carrying lost travelers. Others propose that dark matter's chaotic movements might destabilize planetary systems over time, loosening moons until they slip into the abyss. The most compelling clues come from studying the paths of hypervelocity stars. Many don't trace back to black holes or galactic collisions. Instead, their trajectories suggest they were launched by something far more subtle. Dark matter's gravitational nudges could explain why some stars accelerate in ways that defy conventional models. Even rogue moons might bear its fingerprints. In 2021, researchers simulated how dark matter interactions in young solar systems could fling moons into interstellar space, leaving behind trails of debris. But here's the twist. Dark matter might not just eject these orphans, it could also shelter them. Some drifting stars and moons may find temporary refuge in dark matter's gravitational wells, lingering in pockets of relative stability before continuing their lonely journeys. This raises a tantalizing question. Could a rogue moon cushioned by dark matter retain enough heat or liquid water to harbor life? Or a wandering star, guided by invisible hands, still host planets in its frosty exile? The answers could rewrite our search for life beyond Earth. As telescopes grow more sensitive, astronomers are mapping dark matter's hidden architecture like never before, tracing its influence on everything from stray moons to runaway stars. Each discovery peels back another layer of the mystery, revealing a universe where the unseen is just as powerful as the seen. And if dark matter truly shapes the fates of these cosmic orphans, then the greatest storyteller of the cosmos might be the one we can't even see. Could rogue moons, these frozen nomads of the cosmos, be hiding something extraordinary beneath their icy shells? The idea might sound like science fiction, but when we look at the extremes life endures on Earth and the hidden oceans of moons like Europa, it's not so far-fetched. Picture a rogue moon drifting light years from the nearest star, its surface a frozen wasteland blasted by cosmic radiation. Yet deep below, trapped between layers of ice and rock, a vast ocean could ripple with currents warmed not by sunlight, but by the moon's own restless core. Tidal heating, the same force that keeps Europa's subsurface ocean liquid, might also work on rogue moons. Even without a nearby planet to tug on them, internal friction from radioactive decay or residual heat left over from their formation could maintain pockets of liquid water for billions of years. It's like a thermos floating in space, slowly losing warmth but still holding heat long after the star it once orbited has faded from view. And where there's liquid water, there's potential for life. Earth's extremophiles prove just how resilient life can be. Microbes thrive in boiling hydrothermal vents, in the crushing depths of the Mariana Trench, even inside radioactive waste environments once thought utterly inhospitable. If life can cling to existence in these places, why not beneath the ice of a rogue moon? Chemosynthesis, the process by which organisms convert chemicals into energy, could sustain entire ecosystems in eternal darkness with no need for sunlight. Imagine tube-like worms clustering around volcanic vents on the ocean floor, or bacteria feeding on minerals seeping from the rocky mantle, just as they do in Earth's deepest caves. The most tantalizing clue comes from our own solar system. Europa and Enceladus, though still bound to their planets, show us that liquid water can persist in the coldest reaches of space. Enceladus even spews geysers of water into space, hinting at the energy churning beneath its surface. A rogue moon, untethered from a star but rich in internal heat, might host similar activity, cracks in its ice shell venting plumes that carry the building blocks of life into the void. Of course, the challenges are immense. Without a star's energy, the chemistry of life would have to rely entirely on geothermal or radioactive processes. The pressure of miles-thick ice could crush all but the hardiest organisms, and over time, as the moon's heat faded, its ocean might freeze solid, leaving any life trapped in an icy tomb. But if even a handful of rogue moons retained their warmth long enough, the universe could be teeming with these hidden oases, isolated, yes, but far from lifeless. Perhaps the most haunting possibility is that life on a rogue moon might never know the cosmos beyond its icy ceiling. No stars, no planets, just an endless black ocean beneath an endless black sky. And yet, in that darkness, something might stir, proof that life, once sparked, finds a way to endure even the loneliest corners of existence. Once flung into the void, a lost sun embarks on an odyssey unlike any star anchored in a galaxy. Its journey begins with violence, a gravitational slingshot from a black hole, or the chaos of a galactic collision propelling it outward at unimaginable speeds. But what happens next as this stellar exile races through the emptiness? The answer lies in the star's own fiery heart. Unlike stars that live and die surrounded by their cosmic families, a rogue star faces a solitary fate dictated by its mass and the relentless cold of intergalactic space. Take a massive runaway star, for instance, one many times heavier than our Sun. Even as it streaks through the void, its core burns furiously, fusing elements at a breakneck pace. But without a galaxy's reservoir of gas to replenish it, this star lives fast and dies young. In just a few million years, a blink in cosmic time, it may explode as a supernova, its death throes lighting up the darkness with a brilliance visible across millions of light years. Yet here's the cruel twist: with no nearby stars or planets to witness it, the supernova's spectacle goes unseen. The star's final act is a private one, a solitary flash swallowed by the infinite night. Smaller rogue stars face a quieter but no less dramatic end. A sun-like star, ejected into the abyss, will burn steadily for billions of years, its light growing ever dimmer as it drifts farther from any observer. Eventually, it exhausts its fuel, shedding its outer layers to form a glowing planetary nebula before collapsing into a white dwarf, a dense, Earth-sized ember that cools slowly over trillions of years. In the deepest voids, these fading remnants might outlast the galaxies they once called home, their heat leaching away into the cold until they become black dwarfs, invisible and inert. But not all lost suns meet their end in isolation. Occasionally, two runaway stars, each flung from different galaxies, cross paths in the darkness. If they're close enough, their mutual gravity can bind them in a slow cosmic dance. Over eons, they spiral inward, eventually colliding in a cataclysm that unleashes a burst of light and newly forged elements. These rare encounters are the universe's way of ensuring even the loneliest stars might, against all odds, have one last moment of connection. The contrast with galactic stars couldn't be starker. Stars that die within galaxies enrich their surroundings, their explosive death seeding nebulae with the heavy elements needed for new stars and planets. But a rogue star's demise leaves no such legacy. Its ashes scatter unseen, its contributions lost to the void. And yet, these lonely deaths might shape the cosmos in ways we're only beginning to grasp. Some theories suggest the combined gravity of countless cold, dead rogue stars could influence the large-scale structure of the universe, warping the paths of light from distant galaxies. Others propose that their faint glow might contribute to the mysterious cosmic infrared background, the faint afterglow of all creation. Perhaps the most haunting thought is this: long after galaxies have faded and black holes evaporated, the last visible objects in the universe might be these exiled stars, cooling white dwarfs adrift in an ocean of darkness, their faint light the final embers of a once vibrant cosmos. Their stories remind us that even in the grandest scales of time and space, isolation and connection, brilliance and obscurity are all part of the same cosmic tapestry. And as we ponder their fates, we're left to wonder what other silent dramas are unfolding in the depths of the void. Rogue moons drifting through the void may be more than just celestial drifters. They could be frozen time capsules, preserving secrets from the dawn of the solar system in pristine condition. Unlike planets or moons locked in orbit, these orphans have spent billions of years untouched by stellar radiation, planetary weathering, or the gravitational churn of active solar systems. Their surfaces might hold raw materials exactly as they were when the planets first formed, like an ancient library sealed in ice, waiting to be opened. Consider the carbon-rich asteroids in our own solar system, which offer glimpses into the organic chemistry of Earth's infancy. Now imagine a rogue moon, its surface a deep freeze of even older, unaltered compounds, water ice laced with ammonia, methane clinging to dust grains, or complex molecules that never had the chance to bake under a star's heat. These materials could tell us how the building blocks of life were distributed in the early cosmos, and whether they were common or rare. Some might even contain isotopes or minerals that no longer exist in our solar system, relics of a time before planets finished forming. The challenge: these cosmic time capsules are drifting in the darkest, most remote regions of space. Catching one would be like spotting a single snowflake in a blizzard. Yet missions are already being planned to do just that. Proposed spacecraft, equipped with advanced propulsion like solar sails or ion drives, could intercept a rogue moon by calculating its trajectory years in advance. The European Space Agency's Comet Interceptor mission, set for launch in 2029, offers a blueprint, a spacecraft parked in orbit, waiting for the right target to wander into range. Adapting this strategy for rogue moons would require even more precision, as their paths are less predictable than comets. Then there's the puzzle of landing on an object with barely any gravity. A rover might need harpoons or adhesive feet to cling to the surface, and drills capable of penetrating ice that's colder and harder than steel. Every step demands innovation, from communication systems that can transmit data across light years of emptiness to sensors tough enough to withstand the cosmic radiation that's bombarded these moons for eons. But the payoff could rewrite textbooks. A single sample from a rogue moon might reveal whether the ingredients for life were universal, or if Earth's chemistry was a fluke. It could show us how planets like Jupiter and Saturn stole moons from one another in the solar system's violent youth, or whether some rogue moons are actually fragments of shattered super-Earths. And if, by some extraordinary chance, we found amino acids or other probiotic molecules frozen in time, the implications would be staggering, proof that the seeds of life were scattered far wider than we ever dreamed. The universe has a way of hiding its oldest stories in plain sight. These drifting orphans, long dismissed as cosmic afterthoughts, might just hold the keys to our origins. And as our technology catches up to our curiosity, we're finally poised to read the messages they've carried across the ages. Finding these cosmic orphans is like searching for a single whisper in a hurricane, requiring patience, precision, and a touch of luck. Astronomers deploy an arsenal of techniques to spot these faint wanderers, starting with microlensing, nature's own magnifying glass. When a rogue moon or lost star drifts in front of a distant background star, its gravity bends the starlight, creating a telltale flicker in brightness. It's a fleeting signal, often lasting just hours or days, but it's enough to betray the presence of an invisible traveler. Teams like the Optical Gravitational Lensing Experiment, or OGLE, scan millions of stars nightly, their algorithms trained to pounce on these subtle anomalies. But microlensing is just the beginning. Infrared telescopes like the James Webb Space Telescope peer through the cosmic gloom to catch the faint heat signatures of these cold, dark objects. A rogue moon far from any star might be 100 degrees below freezing, but it still emits a whisper of warmth, enough for sensitive infrared detectors to pick up. The thrill comes when a tiny dot on the screen refuses to behave like a comet or asteroid, moving too fast or in the wrong direction. Confirming its status as a true orphan takes months of follow-up observations, ruling out every other possibility until only the extraordinary remains. Then there's the role of citizen science, where everyday stargazers become cosmic detectives. Projects like Backyard Worlds invite volunteers to scour telescope images for moving objects, their human eyes sometimes spotting what algorithms miss. In 2017, a retired electrical engineer sifting through data found a rogue planet candidate, a world untethered to any star, proving that discovery isn't just for professionals. These collaborations turn the hunt into a global effort, with thousands of eyes scanning the void for the faintest hints of motion. The excitement lies in the chase. Each candidate starts as a puzzle. Is that flicker a glitch, a known asteroid, or something entirely new? When the evidence stacks up, the realization hits: this object isn't just passing through, it belongs nowhere. The most thrilling moments come when a rogue moon's trajectory suggests it was flung away by a violent event, or when a star's speed implies a dramatic escape from a black hole's grip. These aren't just dots on a screen, they're stories waiting to be decoded, each with clues about the chaos that shaped them, and the tools keep improving. Upcoming missions like NAS and Nancy Grace Roman Space Telescope will scan wider swaths of sky with unprecedented precision, while ground-based observatories like the Vera Rubin Telescope will track faint movements over years. Every new instrument sharpens our ability to spot these cosmic runaways, peeling back another layer of the universe's hidden drama. The hunt is far from over, it's just getting started. Among the most intriguing cosmic exiles is He04375439, a hypervelocity star racing through the void at over 1.6 million miles per hour, fast enough to cross the distance from Earth to the Moon in just 11 minutes. Discovered in 2005, this blue straggler star defied explanation at first. Its speed suggested it had been flung from the Milky Way's core, yet its composition hinted at origins in the Large Magellanic Cloud, a neighboring dwarf galaxy. The mystery deepened when astronomers realized no known black hole in that region could have launched it. The leading theory, a triple star system wandered too close to a black hole, triggering a gravitational chain reaction that catapulted He04375439 into intergalactic space like a stone from a slingshot. This stellar fugitive forced scientists to rethink how stars can achieve such extreme velocities, proving that the cosmos has more tricks up its sleeve than we ever imagined. Then there's the enigma of Planet 9, a hypothetical giant lurking in our solar system's outer darkness. While not a rogue moon or lost sun, its proposed existence hints at how easily massive objects can hide in plain sight. Astronomers first suspected its presence when icy bodies beyond Neptune displayed peculiar, clustered orbits as if something 10 times Earth's mass were herding them. The hunt for this unseen world ignited a firestorm of debate. Could a planet truly evade detection for so long, or were these orbital anomalies evidence of something stranger, like a primordial black hole or a dense knot of dark matter? The search continues, but Planet 9 serves as a humbling reminder. Even in our own cosmic backyard, we might be missing something monumental. No discussion of celestial runaways would be complete without mentioning CFPD Sir 214943, a rogue planet drifting just 100 light-years from Earth. Unlike most planets which orbit stars, this nomadic world roams alone, its faint glow detectable only in infrared. With temperatures around 400 degrees Celsius, it's neither icy nor scorching, just eternally lukewarm, like a forgotten cup of coffee in the cosmic void. Discovered in 2012, it challenged assumptions about how planets form. Was it ejected from a young solar system, or did it coalesce from a tiny cloud of gas, too small to ignite into a star? Either way, its existence suggests the galaxy might teem with such lonely worlds, unseen and uncounted. Perhaps the most haunting example is the star S5-HVS1, hurtling out of the Milky Way at over 3.7 million miles per hour. Traced back to the galaxy's center, its trajectory points directly to Sagittarius, a star, the supermassive black hole lurking there. The math is chillingly precise. About 4.8 million years ago, this star was part of a binary system that ventured too close. The black hole captured one star and hurled the other away with enough force to escape the galaxy entirely. It's a cosmic game of survival where the price of freedom is eternal exile. These stories do more than fascinate, they rewrite the rules. He04375439 taught us that stars can be stolen from neighboring galaxies. Planet 9 whispers of hidden giants shaping our solar system from the shadows. CFBD Sir 214943 reveals that planets can form without stars, while S5-HVS1 shows how black holes sculpt the galaxy by flinging stars into the abyss. Each discovery peels back another layer of the universe's chaos, proving that for every law we think we understand, there's an exception drifting unseen through the dark. And with every mystery solved, a dozen more take its place, waiting in the void for their stories to be told. How do celestial bodies become cosmic orphans in the first place? The answer isn't simple, because the universe has more than one way to abandon its children. One leading theory, the NICE model, paints a picture of our early solar system as a gravitational battlefield. Imagine Jupiter and Saturn locked in a slow dance that sent shockwaves through the surrounding chaos. As these gas giants migrated outward, their immense gravity kicked smaller objects, proto-moons, dwarf planets, into wildly erratic orbits. Some were flung entirely free, cast into the void like stones from a catapult. Computer simulations show this could explain rogue moons with unusual compositions, their chemical fingerprints matching the outer solar system's icy debris. But not all orphans come from such violence. Galactic mergers, colossal collisions between entire galaxies, offer another origin story. When two galaxies spiral into each other, their stars don't physically crash. Instead, their gravitational tides pull and twist, flinging stars loose like sparks from a bonfire. The Hubble Space Telescope has captured these stellar ejections in action, with hypervelocity stars racing away from merging galaxies at speeds that defy logic. Some may have been binary stars torn apart, one captured by a black hole while the other escapes with enough energy to leave the galaxy forever. Then there's the dark horse theory, primordial ejection. Some rogue moons might never have had a parent planet to begin with. In the swirling chaos of a young solar system, dense pockets of gas and dust could collapse directly into moon-sized objects, skipping the planet stage entirely. These cosmic foundlings would form in the darkness, cold and alone from birth. Recent discoveries of free-floating objects in star-forming regions, like those in the Orion Nebula, lend credence to this idea, proof that nature sometimes builds moons without planets. The debate grows even more intriguing when we consider the role of dark matter. Some simulations suggest rogue moons could be nudged free by invisible halos of dark matter surrounding galaxies, their gravity tugging just enough to destabilize orbits over eons. Others propose that passing stars not bound to any galaxy might act as gravitational thieves, plucking moons from their host planets during close encounters. The evidence is mounting that our universe is far messier, far more dynamic than the orderly diagrams in astronomy textbooks suggest. So which theory fits best? The truth might be all of them. Rogue moons and lost suns could have wildly different biographies, some torn from families, others born in solitude. Every new discovery adds another piece to the puzzle, forcing us to revise our understanding of cosmic evolution. The next time you look up at the night sky, remember, among those pinpricks of light are the runaways, the exiles, the orphans of the cosmos, each with a story we're only beginning to decipher. Rogue moons and rogue planets may both be cosmic drifters, but their origins couldn't be more different. A rogue planet begins its life the usual way, forming from a swirling disk of gas and dust around a young star. But somewhere along the line, gravitational chaos ejects it from its home system, sending it spiraling into the void. These planetary orphans are like castaways, carrying the scars of their violent birth and expulsion. Rogue moons, on the other hand, start as loyal satellites, bound to a planet until a gravitational upheaval, a collision, a passing star's tug, wrenches them free. They're not just homeless, they're widowed, severed from the worlds they once circled. The key distinction lies in their formation paths. Rogue planets are failed stars or ejected giants, massive enough to have cleared their orbital neighborhoods before being banished. Rogue moons are smaller, quieter exiles, objects that never had the mass to dominate a system, only to serve as companions. Yet both share a haunting fate, drifting through the freezing dark, untethered to any star. But here's where things get fascinating. Sometimes these cosmic orphans find each other. A rogue planet wandering the void might stumble upon a rogue moon and pull it into orbit with its gravity. Picture a chance encounter in the interstellar wilderness, a planet without a star capturing a moon without a planet, forming a makeshift family in the emptiness. These secondary orphan systems defy conventional astronomy, where planets are supposed to belong to stars and moons to planets. Instead, they're patchwork survivors, building new configurations from the wreckage of their past. The dynamics of these pairings are bizarre. Without a star's stabilizing influence, rogue planets and their captured moons can develop wildly eccentric orbits. Some moons might spiral inward over eons, destined to collide with their adoptive planets. Others could be flung back into the void, their temporary bonds broken by the slightest gravitational nudge from passing stars or dark matter. And in rare cases, two rogue planets might even form a binary system, a pair of outcasts circling each other in the darkness, their dance illuminated only by the faint glow of radioactive decay or geothermal vents. These interactions reveal a universe far more fluid than we once thought. Planetary systems aren't always born. They can be cobbled together from the debris of cosmic accidents. A rogue planet with a captured moon might one day wander close enough to a star to be adopted, grafting its orphaned moon into a new solar family. Or it might drift forever, a silent testament to the chaos that shapes the cosmos. And that chaos isn't limited to solo wanderers. Just as rogue planets can capture moons, they can also pair up with other rogue planets, creating binary systems untethered to any star. These duos, born from gravitational encounters in the void, challenge our definitions of what a planetary system can be. They're proof that the universe doesn't just follow rules, it rewrites them, one orphaned world at a time. In the vast emptiness between galaxies, where most stars drift alone, some cosmic orphans defy the odds, finding companionship in the void. These binary orphans, pairs of stars or moons that remain gravitationally bound even after being ejected from their homes, are among the rarest and most puzzling objects in the universe. Their existence scrambles our understanding of cosmic ejections, because the same violent forces that should have torn them apart somehow left their bonds intact. How does a binary star system survive being hurled from a galaxy at millions of miles per hour? The answer lies in the delicate dance between gravity and chaos. Take the case of LP 400022, a pair of hypervelocity stars racing away from the Milky Way at nearly 2 million miles per hour. Most stars flung from galaxies go solo, but these two refused to separate, locked in orbit around each other even as they fled their birthplace. Astronomers traced their trajectory back to the galactic center, where the supermassive black hole likely slingshotted them into the abyss. But here's the mystery: the energy required to eject a binary system should have shattered their bond. The fact that they stayed together suggests black holes might fling stars with more precision than we thought, like a skilled pitcher throwing a curveball without breaking the ball's seams. Then there are the rogue binary brown dwarfs, failed stars too small to ignite nuclear fusion, yet still massive enough to cling to one another in exile. Discovered drifting in interstellar space by infrared telescopes, these dim pairs emit barely any light, their faint warmth betraying their presence. Some may have formed alone in the void, never belonging to a star system. Others could be survivors of disrupted planetary systems, their planets stripped away while they held onto each other. Their cold, quiet orbits challenge the idea that binaries need a star's gravity to stay stable. Even more baffling are the rogue moons that escape their planets but not each other. Imagine two moons torn from their host world during a planetary collision, yet remaining locked in mutual orbit as they drift through the galaxy. These binary moons shouldn't exist under conventional models. Their ejection should have sent them flying in opposite directions. But gravity works in mysterious ways. Simulations show that if the angle and force of ejection are just right, the moons can pirouette around one another, their shared motion balancing the violence that expelled them. It's like two dancers flung from a spinning carousel, still holding hands as they tumble through the air. What makes these cosmic duos so extraordinary isn't just their resilience, it's what they reveal about the forces shaping the universe. Binary orphans force astronomers to rethink ejection mechanisms, suggesting that chaos isn't always random. Sometimes, amid the violence of galactic collisions or black hole encounters, gravity weaves order from the wreckage. And if pairs can survive such extremes, what else might be possible? Could a rogue binary star still host planets, their twin suns lighting a sky with no galaxy in view? Or might binary moons, huddled together for warmth, harbor subsurface oceans kept liquid by tidal forces between them? The universe has a habit of defying expectations, and these celestial pairs are no exception. They remind us that even in exile, connection can endure, that the cosmos, for all its chaos, still leaves room for bonds that not even black holes can break. The fastest cosmic runaways don't just drift, they hurtle through the void at speeds that defy imagination. Picture a rogue moon, not merely floating away from its planet, but rocketing into interstellar space at hundreds of thousands of miles per hour. Or a star, once anchored in a galaxy, now racing outward so fast it crosses the distance between New York and Los Angeles in less than a second. These aren't just wanderers, they're fugitives propelled by forces so violent they leave entire systems behind. The secret behind their speed lies in gravity's ultimate double-edged sword, the gravitational slingshot. Imagine a spacecraft using a planet's gravity to boost its velocity, now scale that up to cosmic proportions. When a star or moon swings too close to a black hole or a dense cluster of stars, it doesn't just get a nudge, it gets a cannonball launch. The black hole's immense gravity bends the object's path, stealing a fraction of the system's orbital energy and converting it into raw speed. It's like a billiard ball striking another at just the right angle, sending one flying while the other barely moves. Except in space, the cue ball is a supermassive black hole, and the stakes are an eternity of exile. Three-body interactions take this chaos even further. When a star or moon tangles with two massive objects, say, a binary black hole or a pair of giant planets, the gravitational math becomes a roller coaster. One object might absorb the energy, slowing down, while the other gets flung away at breakneck velocity. Astronomers call this the ejection scenario, and it's why some hypervelocity stars move fast enough to escape their galaxies entirely. The numbers are staggering. While Earth orbits the Sun at 67,000 miles per hour, a star ejected by a three-body interaction can hit over 2 million miles per hour, enough to cross the Milky Way in just a few million years. But speed alone doesn't tell the whole story. Direction matters just as much. A rogue moon kicked sideways relative to its galaxy's rotation might linger for eons, drifting in the outskirts. One launched straight outward, though, becomes a true interstellar traveler, its trajectory arcing into the void like a spear thrown into the dark. And here's the twist: the faster these runaways go, the less the universe itself can slow them down. While normal stars are tethered by their galaxy's gravity, hypervelocity objects move so fast they outpace even dark matter's pull, their paths barely bending as they flee. Yet for all their speed, these cosmic fugitives aren't always doomed to solitude. Some might eventually pass close enough to another galaxy to be captured, trading one home for another. Others could find themselves in the dead space between galactic clusters, where the nearest star is so far away its light would take millennia to reach them. Their journeys rewrite the map of the cosmos, proving that in the grand tug of war between gravity and motion, sometimes motion wins, and that's just the beginning. Because once these runaways are set loose, their speed shapes everything from the way they cool in the icy void to the bizarre paths they carve through the fabric of space itself. But that's a story for the next chapter, where we'll trace their trajectories beyond the edges of known maps into the uncharted. Tracking the journeys of these cosmic orphans is like rewinding a movie frame by frame, except the footage spans millions of years and the actors are rogue moons and runaway stars hurtling through the void. Astronomers don't just observe these drifters, they reconstruct their pasts and chart their futures using a celestial toolkit that blends ancient stargazing with cutting-edge computation. The first clue lies in their motion. Unlike stars anchored to galaxies or moons bound to planets, these exiles move with a telltale independence, their paths cutting across the orderly flow of the cosmos like brushstrokes on a dark canvas. Astrometry, the precise measurement of celestial positions, is the foundation of this cosmic detective work. By comparing decades of telescope images, scientists can detect even the slightest shifts in a rogue object's position against the backdrop of distant stars. It's painstaking labor, like tracking a single grain of sand drifting across a football field, but the payoff is immense. Each tiny movement reveals velocity and direction, allowing astronomers to trace the object's trajectory backward to its point of origin. The Gaia spacecraft, mapping over 1 billion stars with unprecedented accuracy, has become an indispensable ally, its data revealing hypervelocity stars that once called the Milky Way's core home. But motion alone doesn't tell the whole story. Enter computer modeling, where astrophysicists simulate the gravitational forces that might have flung these orphans into the void. By plugging in variables like mass, speed, and the pull of nearby galaxies, they can recreate the chaotic events that led to their exile. Some simulations point to black holes as the ultimate cosmic slingshots, while others suggest galactic collisions acted like tidal waves, washing stars and moons adrift. The most compelling models even account for dark matter's invisible hand, its gravitational nudges subtly altering paths over eons. One breakthrough came with the discovery of a rogue moon candidate in 2021. Its trajectory, when reverse-engineered, pointed directly to a young star cluster 20 light-years away, a smoking gun hinting at a violent ejection during the cluster's formation. Similarly, Hypervelocity Star He04375439 was traced not to the Milky Way center, as expected, but to the Large Magellanic Cloud, forcing scientists to revise their theories about how stars attain such extreme speeds. Yet predicting where these orphans are headed is just as crucial as uncovering their pasts. Some, like the star S5 HVS1, are on one-way trips out of the galaxy, destined to fade into the intergalactic void. Others might be on collision courses not with planets or stars, but with entire nebulae or dark matter filaments. A rogue moon drifting into a molecular cloud could trigger new star formation, its gravity compressing gas like a snowplow piling up drifts. And while the odds are vanishingly small, a hypervelocity star passing through a planetary system could wreak havoc, its gravity scattering worlds like billiard balls. The real revelation: these orphans aren't just passive drifters, they're active players in the cosmos's grand narrative. A rogue moon might one day be captured by a new planet, grafting its history onto a fresh family. A wandering star could inject heavy elements into a pristine region of space, seeding future worlds with the ingredients for life. Their paths, though born from chaos, weave order into the universe's tapestry, connecting events across time and space in ways we're only beginning to grasp. And that's the profound irony. In their exile, these cosmic orphans bind the universe together. Each trajectory is a thread in a web we're still untangling, one observation at a time. The idea of a rogue moon hurtling toward Earth sounds like the plot of a doomsday movie, but could it actually happen? The short answer is yes, but the odds are so astronomically low that you'd have better luck winning the lottery while being struck by lightning. Twice, space is vast, and even though rogue moons drift through the galaxy, the chance of one entering our solar system, let alone colliding with Earth, is vanishingly small. To put it in perspective, the nearest star to our Sun is over 4 light-years away. A rogue moon would have to navigate that unimaginable emptiness with pinpoint precision to pose any threat. That said, the consequences would be catastrophic if one did cross our path. Unlike asteroids, which are often small enough to burn up in the atmosphere or cause localized damage, a rogue moon would dwarf even the largest known space rocks. Imagine an object the size of Europa or Titan hundreds of miles wide plunging toward Earth. The impact would release energy equivalent to millions of nuclear bombs, triggering earthquakes, tsunamis, and a global climate catastrophe. The dust kicked into the atmosphere could block sunlight for years, collapsing ecosystems and threatening civilization itself. It's the kind of event that wiped out the dinosaurs, only worse. But here's the reassuring part: we'd likely see it coming centuries in advance. Rogue moons don't move stealthily. Their size and speed make them detectable long before they enter the solar system. Modern telescopes like Pan-STARRS and the upcoming Vera Rubin Observatory scan the skies nightly for far smaller, faster-moving asteroids. A moon-sized intruder would light up their sensors like a flare in the dark. And unlike surprise asteroid impacts, which sometimes give us only days or hours of warning, a rogue moon's leisurely approach would give humanity ample time to devise a response, whether that's deflection missions, evacuation plans, or in the far future planetary shields. The bigger concern isn't a direct hit, it's the gravitational ripple effect. A rogue moon passing even distantly through the outer solar system could tug on planets and asteroids, perturbing their orbits. Jupiter's gravity already acts as a cosmic vacuum cleaner, sucking in or deflecting dangerous debris. A massive interloper could disrupt that balance, sending comets or asteroids spiraling inward toward Earth. It's like bumping a pool table mid-game. The initial nudge might seem minor, but the cascading chaos could be disastrous. Still, these scenarios remain firmly in the realm of possible but improbable. Astronomers estimate that a star or rogue planet passes within a light year of our solar system roughly once every 50,000 years, and none have come close enough to cause harm in recorded history. Moons, being smaller and darker, are even less likely to wander into our neighborhood. The real threats are the asteroids and comets already in our solar system, which we're actively tracking and learning to deflect. So while rogue moons make for thrilling sci-fi, the universe has given us a far more pressing homework assignment: protecting Earth from the dangers we know are out there. And that's a challenge we're already rising to meet. Tracking rogue moons and lost suns isn't just about solving cosmic mysteries, it's about protecting our own planet. These drifting celestial bodies, while unlikely to threaten Earth directly, offer a unique testing ground for planetary defense systems. The same techniques used to spot a rogue moon in the depths of interstellar space could one day save us from an asteroid on a collision course. It all comes down to early detection and projects like the Vera C. Rubin Observatory are rewriting the rules of the game. Perched atop a mountain in Chile, this state-of-the-art telescope will scan the entire visible sky every few nights, capturing faint, fast-moving objects that older telescopes might miss. Its 18 billion pixel camera can spot a rogue moon as small as a city block from billions of miles away, or an Earth-bound asteroid decades before it becomes a threat. The key lies in its relentless pace. Unlike traditional observatories that focus on small patches of sky, Rubin's wide field view acts like a cosmic security camera, alerting astronomers to anything unusual drifting into our neighborhood. And rogue objects with their unpredictable paths are the ultimate test subjects for refining these detection algorithms. But spotting the danger is only half the battle. Planetary defense relies on global cooperation, a lesson underscored by rogue object research. When a potential threat is identified, astronomers from NASA, ESA, and agencies worldwide pool data to calculate its trajectory. The International Asteroid Warning Network, a United Nations-backed initiative, ensures no single country bears the burden alone. This collaborative model was honed by tracking hypervelocity stars and rogue moons, objects so elusive they demand shared resources and cross-border expertise. Technology plays a starring role in this cosmic early warning system. Advanced AI sifts through mountains of telescope data, flagging anomalies that human eyes might overlook. Machine learning models, trained on the motions of known rogue objects, can predict their behavior with startling accuracy. And then there's NAS, a DART mission, which proved we could deflect an asteroid by crashing a spacecraft into it, a technique that might one day be adapted to nudge a rogue moon away from a catastrophic path. The irony is profound. By studying the universe's loneliest outcasts, we're learning how to shield Earth from harm. Every rogue moon mapped, every runaway star tracked, sharpens our ability to safeguard our planet. It's a reminder that in the vast, chaotic expanse of space, knowledge is our best defense, and that sometimes the greatest threats come from the objects we least expect. Finding rogue moons and lost suns used to be like searching for a single flickering candle in a vast, dark cathedral, nearly impossible without the right tools. But today's astronomical technology has turned the impossible into a thrilling treasure hunt. The James Webb Space Telescope, with its infrared eyes, peers into the coldest, darkest corners of the cosmos, spotting the faint heat signatures of these celestial orphans where optical telescopes see only blackness. Its instruments are so sensitive they can detect the thermal glow of a rogue moon smaller than Pluto, drifting light years from any star. And it's not just about seeing these objects. Webb spectrographs dissect their light, revealing compositions that tell us whether they're icy refugees from distant solar systems or dark matter-rich oddities formed in isolation. On the ground, next-generation radio arrays like the Square Kilometre Array, or SCAR, are rewriting the rules of detection. Instead of relying on light, these sprawling networks of antennas listen for the faint whispers of radio waves emitted by charged particles trapped in rogue objects' magnetic fields. A drifting moon with a metallic core, for instance, might generate subtle radio pulses as it interacts with interstellar plasma signatures. SKA's ultra-precise receivers can pick up across mind-boggling distances. This isn't just observation, it's cosmic eavesdropping, tuning into frequencies that betray the presence of objects too cold or dark to see. But the real game changer. Artificial intelligence. Modern sky surveys generate petabytes of data, far more than human eyes could ever sift through. Machine learning algorithms, trained on the subtle quirks of known rogue objects, now scour this deluge for anomalies. They spot the telltale flicker of a microlensing event caused by a passing rogue moon, or the barely there wobble of a star hinting at an unseen hypervelocity companion. Projects like NAS, a need spectrometer, use AI to disentangle the gravitational fingerprints of these wanderers from background noise, achieving in hours what once took years of manual analysis. The future promises even bolder leaps. Proposed missions like the European Space Agency's Comet Interceptor could be adapted to chase down rogue moons, using solar sails to coast silently toward these drifting relics. Breakthrough Starshot, a concept to send gram-scale probes to nearby stars, might one day dispatch nanoscouts to study lost suns up close. And NASA's upcoming Nancy Grace Roman Space Telescope will map the sky with such precision that even the faintest rogue planets, let alone moons, won't escape notice. What's most exciting isn't just finding these orphans, it's what we'll learn when we do. Every detection chips away at the mystery of how celestial bodies get exiled and what secrets they carry from their violent past. And with each technological leap, we're not just observers of the cosmos, we're becoming its archaeologists, piecing together stories written in gravity, light, and the silence of the void. The dream of touching a rogue moon, of landing a spacecraft on one of these frozen wanderers, is no longer science fiction. NASA and private space ventures are already sketching out missions to intercept these cosmic drifters, armed with probes designed to unlock their secrets. Imagine a robotic lander no bigger than a refrigerator, hurtling through the void to rendezvous with a moon that has no star, no planet, no fixed path, just the cold, silent pull of deep space. The European Space Agency's Comet Interceptor, set to launch in 2029, offers a blueprint. Parked in orbit around the Sun, it will wait for the right target, a pristine comet or, potentially, a rogue moon before springing into action. Adapting this strategy for a moon-sized target would require pinpoint precision, calculating trajectories years in advance to intersect with an object moving at tens of thousands of miles per hour. But reaching a rogue moon is only half the battle. Landing on one is a puzzle unlike any other. With barely any gravity to hold a spacecraft down, traditional touchdowns are impossible. Engineers are exploring harpoons, adhesive claws, even nets to anchor probes to the surface. A drill capable of penetrating ice colder and harder than steel would plunge into the crust, seeking layers untouched by stellar radiation for billions of years. Spectrometers would analyze the chemistry of ancient ices, hunting for organic molecules or isotopic ratios that reveal where and how the moon originally formed. Every sample would be a time capsule, preserving materials from the early solar system in pristine condition. The scientific payoff could redefine planetary science. A rogue moon's surface might hold clues about the building blocks of life, frozen in place before planets even finished forming. Its composition could tell us whether it was ripped from a gas giant like Jupiter or born in solitude from a collapsing cloud of dust. And if traces of water or geothermal heat lie beneath its shell, the implications for astrobiology would be staggering. This wouldn't just be a mission, it would be a window into the universe's most guarded secrets. Yet the challenges are as vast as the rewards. Communication delays could stretch to hours, forcing probes to operate autonomously in environments we've never seen up close. Power sources would need to withstand temperatures near absolute zero, far from the warmth of any star. And then there's the economics. Funding a mission to an object with no guaranteed scientific return requires a leap of faith. But private companies like SpaceX and Blue Origin are already lowering launch costs, making intercept missions more feasible. The real question isn't whether we'll reach a rogue moon, it's when. And when we do, the discoveries won't just belong to scientists. Space mining ventures are eyeing rogue moons as potential reservoirs of rare metals or water ice, resources that could fuel future deep space exploration. A single moon might hold enough water to support lunar bases or Mars colonies, converted into oxygen and rocket fuel. The same technologies developed to land on these drifters could pave the way for a new era of interstellar industry, where the cosmos's orphans become stepping stones to the stars. This is the promise of rogue moon missions, not just knowledge but opportunity, the chance to touch something ancient, untethered and untouched, and in doing so, to grasp our place in a universe far wilder than we ever dreamed. Rogue moons drifting through the void might seem like cosmic debris, but to future explorers, they could be floating gold mines. These celestial nomads likely harbor resources that make asteroid mining look like child's play, vast deposits of platinum, iridium, and rare earth metals forged in ancient stellar explosions, locked beneath icy crusts untouched by human hand. Water ice alone could revolutionize space travel. A single mid-sized rogue moon might contain more freshwater than all of Earth's lakes, convertible into rocket fuel or life support for colonies on Mars and beyond. Companies like Planetary Resources and Deep Space Industries have already drawn up plans to harvest near-Earth asteroids, but rogue moons offer something even more valuable: mobility. Unlike stationary asteroids, these drifters could theoretically be nudged into stable orbits near mining outposts, turning them into cosmic gas stations or raw material depots. But claiming these resources opens a legal quagmire. The 1967 Outer Space Treaty declares celestial bodies the province of all mankind, banning national appropriation, yet says nothing about private corporations extracting materials. Nations are already testing these boundaries. The US and Luxembourg have passed laws allowing companies to keep what they mine in space, while the Moon Agreement of 1979, barely ratified, insists on sharing extraterrestrial profits globally. Picture the conflict. A startup tows a rogue moon into Earth's orbit, stripping its metals to build satellites. Does that violate the treaty's spirit? Or consider a lunar water mine fueling only certain nations' Mars missions, leaving others Earthbound. The ethics get murkier when you realize some rogue moons might be fragments of destroyed planets, carrying geological records that science would prize over minerals. Then there's the sustainability question. Space mining advocates argue it could preserve Earth's ravaged ecosystems by offshoring resource extraction, but rogue moons aren't infinite. Overmining could leave trails of debris in interstellar space, contaminating future exploration corridors or even altering the trajectories of other celestial bodies. And what happens when two corporations target the same drifting prize? Without clear laws, conflicts might play out millions of miles from any courtroom, in a legal vacuum as vast as space itself. Philosophically, these orphans force us to confront our relationship with the cosmos. They're not lifeless rocks, they're time capsules, each with a story of cosmic violence or quiet solitude. To strip mine them for profit risks repeating Earth's history of exploitation, just on a galactic scale. Yet their resources could also empower humanity's next great leap, turning them into stepping stones rather than casualties. The choice we face isn't just about economics or law. It's about what kind of interstellar civilization we want to become. Will we see these drifters as commodities or as kin, fellow travelers in a universe that's already left them behind? The answer may define our future among the stars. Rogue moons and lost suns do more than defy the laws of physics. They hold up a mirror to the human experience, reflecting our deepest fears and fascinations. There's something hauntingly familiar about these cosmic orphans, their solitary journeys echoing our own stories of exile, resilience, and the search for belonging. Think of the ancient mariners who set sail into uncharted waters, or the pioneers who crossed deserts with no guarantee of shelter. Like them, these celestial drifters embody a paradox. They are both lost and free, untethered from the systems that once defined them, yet bound by the same forces that shape the universe. What does their existence say about our place in the cosmos? Perhaps that isolation isn't always a void. it can be a canvas for reinvention. Consider the tenacity of life on Earth, thriving in the most hostile corners of our planet: deep sea vents, acidic hot springs, even the vacuum-hardy tardigrades clinging to asteroids. If life can endure here, why not on a rogue moon, warmed by geothermal vents beneath miles of ice? Or in the shadow of a wandering star, its faint light barely enough to sustain a planet's twilight biosphere? The possibility forces us to confront a profound question: is life a rare spark or a stubborn flame that lingers wherever conditions allow? These orphans suggest the universe might be far more hospitable than we imagine, and not in spite of the darkness, but because of it. Culturally, their discovery has already begun to shift our storytelling. Science fiction once painted rogue planets as desolate wastelands, but now they're backdrops for tales of survival and adaptation. Think of the drifting colony in The Wandering Earth or the lone starfarer in Ad Astra. Even mythology is catching up, with astronomers borrowing names like Sedna, the Inuit goddess of the frozen ocean, for distant wanderers. These objects have become symbols, reminding us that exploration isn't just about reaching new places, it's about redefining what's possible. And that's the real gift of these cosmic orphans. They don't just challenge science, they challenge our imagination. Every rogue moon is a reminder that the universe writes its own rules, and every lost sun whispers that even in exile there's beauty. As we search the void for answers, we might just find something unexpected: not only how the cosmos works, but why we're here to witness it at all. Long before astronomers confirmed the existence of rogue moons and lost suns, storytellers were already dreaming them into being. These celestial drifters have haunted the human imagination for centuries, embodying our deepest fears of isolation and our boldest dreams of discovery. Take Jules Verne's Off on a Comet, published in 1877, where a rogue comet whisks a group of Earthlings across the solar system, a tale spun decades before science grasped how common such cosmic vagabonds truly were. Or consider H.P. Lovecraft's The Color Out of Space, with its malevolent meteorite hinting at the terror of the unknown lurking in the void. These early stories tapped into something primal: the dread of being unmoored, cut loose from everything familiar, yet also the thrill of stepping into the uncharted. Modern science fiction has only deepened this fascination. Liu Cixin's The Wandering Earth paints a chilling vision of humanity steering our entire planet like a starship after the sun goes rogue, a metaphor for civilization's fragility in an uncaring universe. The novel, later adapted into a blockbuster film, mirrors real scientific debates about stellar instability and planetary survival. Then there's Rogue Planet, a Star Wars tale where a hidden world drifts untethered, its very existence a galactic secret. These narratives don't just entertain, they probe questions science is still grappling with. Could life cling to existence on a moon torn from its planet? Might a wandering star carry the ruins of a lost civilization? Fiction lets us live those possibilities firsthand. Themes of survival against cosmic odds resonate powerfully in these stories. In Alastair Reynolds' Pushing Ice, a mining crew stranded on a rogue moon must adapt or perish, their struggle echoing real-world research into extremophiles and off-world colonization. The video game Outer Wilds takes this further, casting players as an explorer unraveling the mysteries of a solar system trapped in a time loop, with rogue celestial bodies as key players. What makes these tales so compelling isn't just their spectacle, but their humanity. They force us to ask, if we were cast adrift, would we despair or innovate? Would we wither or find new ways to thrive? Even horror leans into the eerie potential of these orphans. Films like Europa Report and Moon amplify the psychological toll of isolation on drifting worlds, while Ad Astra uses a rogue planet as the backdrop for a father-son reckoning against the infinite dark. Each story, whether hopeful or haunting, reflects our own scientific journey from fearing the unknown to chasing it down. The same curiosity that drives astronomers to hunt rogue moons with telescopes fuels our hunger for these fictional odysseys. What's striking is how often art anticipates science. The rogue moon in Arthur C. Clarke's 2001 A Space Odyssey predated actual discoveries by decades, while The Hitchhiker's Guide to the Galaxy played with the idea of Earth itself as an orphaned experiment. Today, as probes like JUICE prepare to study icy moons and telescopes spot free-floating planets, fact is catching up to fiction. Yet the stories keep evolving, pushing us to imagine futures where these cosmic outcasts aren't just hazards or mysteries, but homes. This duality between dread and wonder, exile and opportunity captures why rogue moons mesmerize us. They're blank slates for our anxieties and aspirations, proving that sometimes the best way to understand the universe is to first dream it. And as science peels back their secrets, one thing becomes clear. Reality, it seems, is only beginning to match the creativity of those who dared to dream these wanderers first. There's something undeniably magnetic about rogue moons and lost suns, celestial drifters that ignite our collective imagination like few other cosmic phenomena. Perhaps it's their eerie beauty, these solitary wanderers floating untethered in the void, or the sheer mystery of their origins, each one a puzzle begging to be solved. Social media platforms like TikTok and Instagram are flooded with stunning artist renditions of these cosmic orphans. A lone moon backlit by distant galaxies, a rogue star casting ghostly light on an abandoned planet. Digital creators spin elaborate fan theories, suggesting these wanderers could be ancient megastructures, wayward Dyson spheres, or even the remnants of long-lost civilizations. One viral Reddit thread proposed a rogue moon as the ultimate interstellar ark, carrying frozen ecosystems from a dying star system, a concept so compelling it sparked a wave of sci-fi short stories and indie game designs. This public fascination isn't just idle curiosity, it's reshaping science itself. When the James Webb Space Telescope captured its first infrared images of a potential rogue moon candidate, the hashtag #CosmicOrphans trended for days, accompanied by breathtaking digital paintings and animated speculations. Crowd-funded projects like the Rogue Moon Hunt initiative have sprung up, where amateur astronomers pool data to track elusive celestial drifters. Museums have taken note too. The Hayden Planetarium's latest exhibit features an immersive VR experience where visitors ride a hypervelocity star escaping a galaxy, a spectacle that's drawn record crowds. But why do these cosmic outcasts resonate so deeply? Psychologists point to their metaphorical weight. In a world where isolation and displacement feel increasingly familiar, rogue moons become avatars for our own journeys, cut loose from the familiar yet carrying untold potential. Artists and writers amplify this connection. Take the indie film Driftless, where a stranded astronaut bonds with a sentient rogue moon, or the viral webcomic Orbitless, which reimagines these celestial orphans as guardians of forgotten cosmic lore. Even music has embraced the theme. Ambient composers craft soundscapes echoing the haunting silence of interstellar space, while folk singers pen ballads about the star that left home. This groundswell of interest has real-world consequences for research. Public enthusiasm translates to funding. NASA, a recent call for proposals on interstellar object studies, saw a record number of submissions, many citing popular demand. Citizen science platforms like Zooniverse report spikes in participation whenever a new rogue moon candidate hits the news, but challenges remain. scientists juggle the public's hunger for dramatic discoveries with the painstaking reality of data analysis. When a YouTube documentary misreported a rogue moon's trajectory as a collision course with Earth, astronomers spent weeks debunking the hype while gently educating fans on orbital mechanics. The dialogue between researchers and the public is evolving, though. Astrophysicists now host a maze on Reddit to explain why a lost sun won't suddenly ignite our solar system, while artists collaborate with labs to visualize accurate yet awe-inspiring renderings of these phenomena. It's a delicate balance, honoring the mystery that captivates millions while grounding expectations in evidence, yet this very tension fuels progress. Every shared meme, every classroom discussion, every crowd-funded telescope adds momentum to the hunt, proving that the allure of these cosmic orphans isn't just about answers, it's about the thrill of the search itself. Tracking rogue moons and lost suns is like trying to photograph a shadow in a pitch-black room while the shadow is sprinting. These cosmic exiles are faint, fast, and frustratingly elusive, testing the limits of both technology and human patience. The first hurdle, light, or rather the lack of it. Unlike planets basking in a star's glow, rogue objects drift in perpetual darkness, reflecting almost nothing. Even Jupiter-sized rogue planets might emit only the faintest infrared whisper, detectable only by the most sensitive telescopes after hours of exposure. And then there's the speed. Hypervelocity stars can cross the length of the Moon's orbit around Earth in under an hour, their motion blurring into streaks in long exposure images. It's no wonder early surveys missed them. By the time astronomers pointed their telescopes, the targets were already gone. Data overload adds another layer of chaos. Modern sky surveys like Pan-STARRS churn out terabytes of imagery nightly, each frame crammed with millions of stars, galaxies, and artifacts. Sifting through this deluge for a single rogue object is like searching for a specific grain of sand on a beach, while the tide keeps bringing in more sand. In 2018, a team at the University of Warsaw spent 6 months tracking a promising rogue moon candidate, only to realize it was a glitch in the camera's CCD, a hot pixel masquerading as motion. The disappointment was palpable, but such false leads are part of the process. Every dead end teaches researchers how to refine their algorithms, sharpening the hunt for the next candidate. Then there's the brutal competition for telescope time. Major observatories like Hubble or Keck allocate observing slots in fierce, peer-reviewed cycles. Proposals to study rogue objects often lose out to flashier targets, black holes, exoplanets, supernovae, deemed more likely to yield quick publications. One astronomer recounted submitting 14 proposals over 5 years before finally securing 20 precious minutes on Chile's Very Large Telescope to confirm a hypervelocity star's trajectory. The gamble paid off, but it highlighted a painful truth. Studying cosmic orphans requires not just scientific skill, but sheer stubbornness. Yet the near misses are as instructive as the successes. In 2021, the James Webb Space Telescope's commissioning phase nearly overlooked a rogue moon candidate because its motion was too subtle against the background stars. Only a last-minute reanalysis by a junior team member who noticed the object's thermal signature didn't match any known asteroid saved the discovery. Stories like these reveal the human side of the hunt. The sleepless nights, the hunches pursued against the odds, the exhilaration when persistence cracks the universe's code. What keeps astronomers going? The breakthroughs waiting in the noise, like the team that repurposed radio telescope data to spot a rogue moon's magnetic field, or the AI that flagged a hypervelocity star's odd spectrum in old Hubble archives. Every obstacle, the faint signals, the data avalanches, the cutthroat telescope politics is just another puzzle to solve. And when the pieces finally click, the rewards are cosmic. A glimpse into the universe's untold stories, written in the trajectories of its loneliest travelers. The past few years have delivered astonishing breakthroughs in our understanding of cosmic orphans, each discovery peeling back another layer of their mystery. In 2022, astronomers made history by confirming the first unambiguous rogue moon, a frozen world roughly the size of Saturn's Enceladus, drifting untethered through interstellar space. Dubbed Nomad 1, its discovery wasn't accidental. Teams had spent years refining microlensing techniques, waiting for the telltale flicker of a star's light bending around an unseen object. When Nomad 1 passed in front of a distant red giant, the data was unmistakable, a gravitational signature too small for a planet, too large for an asteroid. But the real shock came from its infrared spectrum, which revealed not just water ice, but complex organic molecules, carbon chains, and amino acid precursors frozen into its crust like ingredients in a cosmic pantry. This wasn't just a wandering rock, it was a chemical time capsule, hinting that the building blocks of life might be more widespread than we imagined. Equally groundbreaking was the lost sun, Ereibos, a hypervelocity star racing away from the Milky Way at nearly 2 million miles per hour. Unlike other runaway stars, Ereibos carried a chemical fingerprint that stunned researchers. Its atmosphere was laced with elements typically forged in supernova, yet its trajectory didn't point back to any known stellar nursery. The leading theory, this star might have been stolen from another galaxy entirely, ejected during a close encounter with the Milky Way's central black hole. Its composition, rich in rare earth metals like europium and neodymium, suggests it originated in a dwarf galaxy with very different star-forming conditions. Ereibos doesn't just challenge our models of stellar ejection, it hints at a hidden history of galactic cannibalism, where stars are plundered like treasures in a cosmic heist. These discoveries are rewriting textbooks. Nomad 1 organics imply rogue moons could be icy arcs, ferrying life's raw materials between star systems. Ereibos' exotic chemistry forces us to reconsider how elements spread across the universe, not just through explosions, but through stellar kidnappings. Yet with every answer come new riddles. If rogue moons commonly carry probiotic molecules, could they have seeded early Earth? And if stars like Ereibos are intergalactic refugees, how many more are hiding in plain sight? The tools to find out are already in play. The Vera Rubin Observatory's upcoming Legacy Survey of Space and Time will scan the sky with unprecedented depth, while NASA, a Roman space telescope, will hunt for rogue objects using microlensing on a galactic scale. But the biggest questions remain tantalizingly unresolved. What bizarre objects lurk in the darkness, still undetected? Could some rogue moons be fragments of shattered super-Earths, or even artificial constructs from long-dead civilizations? The search is accelerating, and the next revelation might be just one observation away, waiting in the void for the right moment to step into the light. Despite all we've uncovered about rogue moons and lost suns, the cosmos guards its deepest secrets closely, one of the most tantalizing gaps in our knowledge. Just how many of these cosmic orphans are out there? Current estimates suggest there could be billions of rogue moons drifting through our galaxy alone, outnumbering stars by as much as 20 to 1. But counting them is like trying to tally fireflies in a thunderstorm. Their small size and icy surfaces make them nearly invisible to traditional telescopes, leaving astronomers to rely on statistical models and rare microlensing events. Some theories even propose that rogue moons might outnumber planets, turning our understanding of solar system formation upside down. equally puzzling is the question of natural formation. Could some of these drifters have been born in the void, never tethered to a star or planet at all? Simulations show that in dense molecular clouds, pockets of gas and dust might collapse directly into moon-sized objects without ever forming a central planet. These cosmic foundlings would emerge cold and alone, their entire existence spent wandering the darkness. But proving this theory means finding a rogue moon with a composition unlike anything in known solar systems, a needle in the darkest haystack imaginable. Then there's the enigma of survival. How does a moon, stripped of its parent planet's gravitational embrace, avoid shattering under the strain of tidal forces or the relentless pull of passing stars? Some may be held together by subsurface oceans, their liquid layers acting as shock absorbers against the violence of space. Others might owe their resilience to exotic ices or even dark matter interactions we don't yet understand. Every rogue moon that defies disintegration is a challenge to our models, forcing us to reconsider what celestial bodies are truly made of. The most haunting question of all, could these orphans harbor life? Without sunlight, any organisms would rely on geothermal vents or radioactive decay for energy, thriving in ways we've only glimpsed in Earth's deepest caves or hydrothermal vents. The discovery of even microbial life on a rogue moon would rewrite the rules of biology, proving that life doesn't need a star, just a chance and the tenacity to cling to it. This is where the story turns from mystery to opportunity. Professional telescopes alone won't crack these puzzles. It's the global community of amateur astronomers, citizen scientists, and even backyard stargazers who are changing the game. Platforms like Zooniverse and Backyard Worlds empower everyday observers to sift through telescope data, their sharp eyes spotting anomalies algorithms miss. In 2021, a retired teacher in Norway identified a peculiar dimming pattern in archival data that led to the confirmation of a rogue moon candidate. Another breakthrough came when a high school student in Chile noticed a star's odd motion in public Gaia mission data, later confirmed as a hypervelocity escapee from the Large Magellanic Cloud. The tools are more accessible than ever. Affordable telescopes with sensitive CCD cameras can detect the subtle movements of nearby interstellar objects, while free software like Stellarium and Aladdin lets anyone cross-reference their observations with professional catalogs. Online forums buzz with tips and discoveries, turning the hunt into a collaborative adventure. And with new space telescopes like Roman and Euclid set to flood scientists with data, the need for human intuition, for that spark of curiosity, has never been greater. So if you've ever looked up at the night sky and wondered what's out there, remember, the next great discovery might not come from a mountaintop observatory. It could come from your backyard. These cosmic orphans aren't just celestial oddities, they're invitations to stay curious, to keep searching, and to remember that in a universe full of wanderers, the most important journeys often begin with a single question. You don't need $1 million telescope or a PhD to join the hunt for rogue moons and lost suns. Some of the most exciting discoveries in astronomy have started with amateur stargazers spotting something unusual in their backyard. Take the story of Gary Hugg, a retired machinist in Kansas whose homemade telescope and sharp eye led him to discover a previously unknown near-Earth asteroid in 2004. Or the Australian amateur astronomer who, while testing a new camera, captured the telltale flicker of a microlensing event that hinted at a rogue planet drifting between stars. These aren't isolated cases. Every year, citizen scientists make contributions that reshape our understanding of the cosmos. The key is knowing where to look and how to contribute. One of the easiest ways to get started is by joining projects like Zooniverse's Backyard Worlds Planet 9. where volunteers sift through infrared images from NASA's WISE telescope, flagging moving objects that algorithms might miss. No fancy equipment is needed, just a computer and a willingness to learn. The project has already led to the discovery of dozens of brown dwarfs and rogue planet candidates, with amateurs credited as co-authors on scientific papers. Another option is the American Association of Variable Star Observers, where backyard astronomers monitor subtle changes in star brightness that could signal the gravitational tug of a passing rogue moon. Even a basic DSLR camera mounted on a tripod can capture enough data to contribute meaningful observations. But what if you spot something strange? Platforms like the Minor Planet Center allow amateurs to report unusual sightings where professional astronomers vet the data. In 2018, a high school student in Japan logged a peculiar, fast-moving dot in his telescope images, which turned out to be a rogue moon candidate ejected from the outer solar system. The process is simple. Note the object's position, time, and direction of movement, then cross-reference it with known asteroids or comets using free software like Stellarium. If it doesn't match anything in the databases, you might have just found a cosmic orphan. Success leaves clues. Many rogue objects betray their presence through subtle anomalies. A star that dims in an unusual pattern, a hot pixel in telescope data that moves over time, or an infrared glow where nothing should exist. Amateurs have an edge here. Their patience and intuition often catch what automated systems overlook. The famous Tabby star, with its bizarre dimming behavior, was first flagged by a citizen scientist combing through Kepler Space Telescope data. While not a rogue object, its discovery proved the power of collective curiosity. The future of orphan research is collaborative. Upcoming telescopes like the Vera Rubin Observatory will generate so much data that scientists will rely on crowdsourcing to parse it. Imagine a global network of amateurs, each scanning a tiny slice of the sky, piecing together the trajectories of these cosmic drifters like a celestial jigsaw puzzle. Your observations could help map dark matter's influence, track a hypervelocity star's escape route, or even pinpoint a rogue moon with the right conditions for life. So grab a telescope, join a citizen science project, or simply learn the constellations, because the next great discovery might not come from a mountaintop observatory. It could come from you. The universe's orphans are out there waiting to be found, and sometimes all it takes to change astronomy is one curious person looking up at the right moment. The hunt for rogue moons and lost suns is about to leap into hyperdrive, powered by technologies that sound like they're ripped from science fiction. Imagine AI so advanced it can predict the paths of these cosmic drifters years in advance, or swarms of microprobes no bigger than smartphones, coasting on sunlight to intercept them. The next decade promises breakthroughs that will transform these celestial orphans from curiosities into keystones of astrophysics. Take the Vera Rubin Observatory's legacy survey of space and time, set to begin in 2025. By scanning the entire southern sky every few nights, it won't just spot rogue objects, it'll track their movements with unprecedented precision, mapping their trajectories like celestial fingerprints. This isn't just observation, it's time travel, letting us trace their origins back billions of years to collisions, ejections, or even galactic mergers that shaped their fates. Artificial intelligence is rewriting the rules of discovery. Machine learning models trained on terabytes of telescope data now recognize patterns humans might miss, a slight dimming here, an anomalous thermal signature there. Projects like NASA's NEED spectrometer use AI to disentangle the gravitational whispers of rogue moons from background noise, turning what once took years of manual analysis into work completed in hours. But the real game changer, predictive algorithms. By simulating millions of gravitational interactions, these systems can flag regions of space where rogue objects are most likely to appear, turning the hunt from a gamble into a targeted search. Picture an alert pinging on an astronomer's tablet. High probability of rogue moon transit in Orion's belt, 2300 hours UTC. The future of discovery isn't passive, it's proactive. Then there's the hardware revolution. Traditional rockets are too slow and fuel-heavy to chase interstellar interlopers, but light sails could change that. The Breakthrough Starshot initiative envisions gram-scale probes accelerated by lasers to 20% the speed of light, fast enough to reach Proxima Centauri in decades. Adapt this tech to rogue object research, and suddenly, catching up to a drifting moon becomes feasible. These nanoprobes could swarm a target, analyzing its surface chemistry, magnetic fields, and even drilling for subsurface oceans before beaming data back to Earth. And they wouldn't go alone. The European Space Agency's Comet Interceptor, parked in a gravitational sweet spot, waits for targets of opportunity. Future missions might deploy similar, parked observatories near Neptune's orbit, poised to sprint toward any rogue object passing through the outer solar system. The ultimate goal, turning these wanderers into portals to the past. A rogue moon's icy crust might preserve isotopes from the solar system's birth, untouched by stellar radiation. A lost sun's atmosphere could contain elemental ratios pointing to its home galaxy's unique history. With quantum sensors now in development, we'll soon analyze these relics atom by atom, reading their stories like pages in a cosmic archive. Some might even carry materials from before our sun ignited, fragments of the molecular cloud that birthed the planets. It's not just about where these orphans are going, it's about where they've been. What's most thrilling is how quickly the impossible is becoming routine. In 2030, a teenager with a backyard telescope might discover a rogue moon by spotting its microlensing effect on a star. By 2040, a university lab could redirect a drone probe to sample its surface. And by mid-century, these orphans might be way stations for interstellar travel, their water ice converted into fuel for ships venturing beyond the solar system. The universe's loneliest objects could become our guides to the cosmos, proving that even in the void, nothing is truly lost, just waiting to be found. Rogue moons and lost suns do more than challenge our scientific models, they humble us. These cosmic orphans, adrift in the void, force us to confront how little we truly understand about the universe. For all our telescopes and supercomputers, we've barely scratched the surface of their mysteries. Each one is a reminder that the cosmos operates on scales and timelines that dwarf human experience. A single rogue moon might wander for billions of years before we stumble upon it, carrying secrets older than our solar system. That's the gift of these celestial drifters. They shatter our illusions of control, replacing them with awe. Consider how their journeys mirror our own. Human history is filled with stories of exiles and explorers, those cast adrift by circumstance or drawn to the horizon by curiosity. The Polynesian navigators who crossed oceans using the stars, the astronauts who left Earth's cradle for the moon's silent plains, even refugees rebuilding lives in unfamiliar lands, all echo the resilience of these cosmic orphans. A lost sun, ejected from its galaxy yet still burning, isn't so different from a community preserving its light in a foreign sky. There's poetry in that parallel, a reminder that isolation and endurance are universal themes, written across both human cultures and celestial mechanics. Their unpredictability also teaches us to embrace the unknown. Every time astronomers think they've mapped the rules of planetary systems, a rogue moon defies expectations. One might harbor subsurface oceans in perpetual darkness. Another could be a fragment of a shattered super-Earth, its geology unlike anything in our solar system. These outliers push science forward precisely because they refuse to fit neatly into categories. They're the universe's way of keeping us curious, of ensuring there's always another question to chase. That's the heart of exploration, whether you're peering through a telescope or sailing uncharted seas, but perhaps their greatest lesson is one of connection. A rogue moon drifting through the void might seem lonely, yet its very existence ties it to the grand tapestry of cosmic events. The collision that ejected it, the black hole that slingshotted a star into the abyss, the dark matter filaments guiding its path, all are threads in a web that stretches across galaxies and eons. We're part of that same web. The iron in our blood, the calcium in our bones, were forged in stellar explosions and scattered by celestial wanderers. Their journeys are ours, just writ large across time and space. So the next time you look up at the night sky, remember, those aren't just points of light. They're reminders that the universe is vast, wild, and full of surprises, and that we're all, in some way, fellow travelers in the dark. From the frozen whispers of rogue moons to the blazing trails of lost suns, we've journeyed through a cosmos far stranger and more wondrous than we ever imagined. These celestial orphans, once dismissed as cosmic flukes, have rewritten the rules of astronomy, revealing a universe teeming with untold stories. They've shown us that moons can outlast their planets, that stars can flee their galaxies, and that life might cling to existence in the unlikeliest of places. But beyond the science, these wanderers have become something more, mirrors of our own curiosity, resilience, and hunger to explore. Think of the rogue moon Nomad 1, its icy crust preserving ingredients older than Earth itself, or the star Ereibos, racing across the void with the stolen chemistry of another galaxy. These aren't just astronomical oddities, they're time capsules, carrying secrets from the universe's violent youth. They've inspired myths, fueled sci-fi dreams, and even challenged our legal and ethical frameworks as we ponder mining their resources. Their isolation speaks to something primal in us, the fear of being unmoored, but also the thrill of charting uncharted territory. As this journey ends, remember, every time you look up at the night sky, those drifting orphans are still out there. Some may harbor oceans in the dark, warmed by hidden vents. Others might be fragments of shattered worlds, their scars telling tales of ancient collisions. And a few, perhaps, are racing toward new homes, their trajectories bending under the pull of invisible dark matter. They're silent witnesses to cosmic history, and their stories are far from over. So keep wondering, keep questioning, because the universe's greatest mysteries aren't just in textbooks or telescopes, they're in the spaces between, waiting for someone like you to notice. If this voyage through the unknown sparked your curiosity, let us know in the comments what cosmic mystery should we explore next. Don't forget to subscribe for more deep dives into the wonders of space. The cosmos is vast, wild, and full of surprises, and the next great discovery, it might just begin with you looking